All right, so now we're going to talk about properties of polynomial interpolation. Okay, so let me state one of the theorems. So the theorem is as follows, that if x0 to xn are n plus 1 distinct points, and f of x is defined at those points, there exists a unique polynomial p of x of degree at most n such that p of x interpolates f which is to say that p at xi is equal to f at xi, I goes from 0 to n. Okay, and the proof of this is relatively straightforward. Right, so let's assume towards contradiction that there is another polynomial which interpolates this. So this is a polynomial degree n such that q xi equals to f at xi, I goes from 0 to n. All right, so we know that p minus q is again a polynomial of degree n. Okay, let's call that r. All right, and r has the following property. So r at xi is equal to p at xi minus q of xi, which is equal to f of xi minus f of xi by the interpolation property, which is equal to 0, and this is true for I equals to 0 to n, right? So that means that R has n plus 1 distinct, well, n plus 1. Well, let me rephrase that. Now, R sort of is 0 at n plus 1 distinct points. Right? But that's not possible because R is a polynomial of degree at most n. So that's only possible that R is 0 at n plus 1 distinct points, but it's a polynomial degree at most n if R is identically 0. Okay, so this implies, again by the fundamental theorem of algebra, that R is identically 0, which means that P is equal to Q. Right? So again, this proves that the interpolating polynomial is unique. Okay? All right. So that's one of the properties of polynomial interpolation, is that it is unique. There may be different representations of the polynomial, but the actual polynomial itself is unique. So let me state another theorem. So if x0, x1, all the way up to xn are distinct points, in the interval from a to b, and f is n plus 1 times continuously differentiable in the interval from a to b, then for each x in this closed interval, there exists a cx in the interval from a to b such that the following is true, that f of x minus Pn of x. So this is the degree n interpolating polynomial is equal to the n plus first derivative at the point cx divided by n plus 1 factorial, and then x minus x0 multiplied all the way up to x minus xn. So if you look at this, this looks very, very similar to the remainder term you have for the Taylor polynomial, right? Because it involves the n plus first derivative of f at some unknown point. And it's like, instead of the product of x minus x0 to the n plus first power, it's the product of x minus x0 all the way up to the product of x minus xn. So it's very, very conceptually similar. And you could sort of imagine that as you let all the points x0 to xn coalesce to x0, so if they all converge to x0, then this, you could imagine gives you a result which is morally like the remainder term that's like for the Taylor polynomial. Okay, and that actually can be made precise. Okay, so and the right way to make it precise is this machinery of divided differences, which we'll talk about in a little bit. So that's another theorem about the remainder. So let me make a few remarks. So the first of which is that, so when you do much beyond linear interpolation, right, the error term which looks like x minus x0, x minus x1, and so on, right, form of the error is not very easy to work with. Okay, and the second observation is the one I had sort of made before, that this remainder term looks conceptually similar. Right, Rn of x is equal to n plus first derivative of f at some unknown point c, which also depends on x in a sense, divided by n plus 1 factorial, x minus x0 to the n plus 1, and then the interpolation remainder term is very similar, but in general for different c's. Then x minus x0 all the way up to x minus xn. Okay, so then the third question is a natural one, is that is there an optimal choice of the x0s to xn? So is there an optimal choice of x0 to xn? And the answer is yes, but it depends on what you mean by optimal. And in particular, we'll see that equally spaced points isn't necessarily always the best ones. So equally spaced points can cause problems. Okay, so we'll see that in a little bit. All right, okay. So, and let me just say one last thing, which is this idea of interpolation versus extrapolation. Okay, so interpolation okay, so let me just say it that way. Sort of the interpolating polynomial Pn of x, right, can be evaluated at any value of x. Okay, and what you do in interpolation is that you choose x to be in the interval from x0 to xn. So if x is somewhere in this interval from x0 to xn, then the error Rn of x is small if x is approximately close to one of the points, right? So if you think about this term here, it's basically the product of the distance from where you evaluated to where all the data points are, right? So if x is somewhere in that interval from x to xn, then hopefully x is close to at least one of these points inside where the data is given, and so the error is going to be small. But with extrapolation, right, then you have that x maybe is less than x0 or x is greater than xn. So Rn becomes large, becomes huge. Okay, because again, you're taking this product of distances. It's like, and if you are outside that interval, then many of those factors are going to be very large in all likelihood. Okay. All right, so what that tells you then is that extrapolation is inherently inaccurate, right? Right, so that's something to be aware of. It's like when you're trying to use data, it's like which is very far away from where you're trying to evaluate or approximate the function at, you'll get an answer which is much more unreliable, which is perhaps obvious, but is nevertheless bears repeating. Okay, so the next thing we're going to do is to sort of talk about more efficient ways of constructing interpolating polynomials, which give you the flexibility of, say, adding more terms. It's like as you have more data, and giving you an expression which is cheaper to compute. All right, so let me just stop here for now.